This is an educational video for the CaNOP program from Carthage College and the Wisconsin Space Grant Consortium. We are designing and building a hyperspectral cube satellite that will monitor forest regions for health and vegetation. This video is on our camera and what types of things we calculated in our initial phase. Our camera is quite small, only a few centimeters tall and a few centimeters wide. The OCI UAV 1000 hyperspectral camera is produced by Basespec and will ensure continuous data collecting from the camera due to its automatic data capturing and processing. It is designed for unmanned aerial vehicles, such as our Cubesat. The camera is able to scan at random speeds, which is beneficial to the project in the sense that as the satellite moves in orbit, its speed will go faster and slower. We are using a Pushbroom scanner. As the satellite moves, the view plane must be perpendicular to the direction of motion. A linear array of sensors will capture data in the form of a hyperspectral cube. This spatial data cube is stacked into spectral bands. It looks like this. The data will be later transferred to the ground. As it flies over the desired area, each line is exposed to a different frequency within the electromagnetic spectrum. Each narrow spatial line is imaged simultaneously, but separated into different levels in frequencies. This data is taken and layered upon one another to create our cube. In hyperspectral imaging, the camera collects information across the electromagnetic spectrum, but also can gather the entire spectrum for each individual pixel of the image. With this, a satellite will be able to identify surface materials, such as different types of vegetation. The electromagnetic spectrum is the collective range of all possible electromagnetic frequencies. This consists of visible light, infrared, and radio waves. Radio waves can be as large as buildings, and gamma rays can be as small as the nuclei of an atom. IFOV, or the instantaneous field of view, is an angle calculation of how much one pixel can see in terms of FOV. The higher the IFOV, the more that will be seen in the image. FOV, or field of view, is the angle describing the area that can be observed at any given moment. The larger the angle, the bigger the size of the observable area. The spatial resolution is the number of pixels in an image. The more pixels, the better the resolution, as seen in the far right picture. Ground sample distance is the length and the width of each pixel. In our case, our pixels are square, so the ground sample distances are the same. Larger ground sample distances have a lower spatial resolution. Spectral resolution is the ability to differentiate wavelength intervals and bands into different components. The lower the resolution, the more sensitive the system is. Scene size measures the distance between the edges of an image, representing the dimensions of the image if it were projected onto the Earth's surface. Pixel size is the length of each pixel that comprises an image, as captured by the camera. Spectral bandwidth is the width of the band of light at 1/2 the peak maximum. Dwell time is the period of time that the camera has to collect a single pixel. Unless otherwise cited, all information is from CaNOP documentation. Thank you for watching our video. Follow us on Facebook, Snapchat, and Instagram. Check back soon for more videos.